Hi, Jungle. Do you got it?
Hello.
Hello.
Yeah.
All right, so we are live. Let me make sure. Email. Yes, it did. Okay. I'm going to give you the host. Do you need anything else from me, Charles?
I think I'm set.
All right. I will speak to you soon.
All right. Take care.
Bye, guys.
Bye-bye. All right. How's it going? If there's anything you typically want to go over, since it's just me and you, you're more than welcome to post it in the chat or whatever. But I do have a notebook planned for this. Oh, whoops, that's not it. I do have a notebook planned for this session. So we'll just continue about as normal. Have you done a session with us before? I can't.
No, it is for my first time. I just graduated. Yeah, finished my course like last Friday, and then yeah.
You graduated from the boot camp or from like college or something?
Boot camp. I was in a boot camp. Yeah.
Oh, okay. Oh, congrats. What was your capstone project?
So I was doing liquor sales analysis in Iowa, and then like do some customer analysis like clustering, and then my goal was what should I say? Like recommendation for location and item categories for new small business owners, something like that. And then yeah.
Oh, okay. Oh, cool. So that was just the 28th cohort, right? Were you doing the full-time or the part-time one?
Yeah, I was in a full-time job, but I think I was in a little bit not popular cohort, so I was pretty much alone, I think.
Oh, okay.
Yeah. So I was in November to March.
Oh, okay. All right. Well, congrats on graduating. I just graduated. I graduated from the run prior to you guys, the September to
yeah. Okay. So you okay? Cool. What was your capstone one?
Good. I mean, it's just me and you, so we can talk about whatever. Okay. Capstone, we did the city bike data set. Do you was that remember? So you get like all the the ride sharing data, and so we analyzed it. We did some k-means clustering, sort of group stations by usage patterns, and then our final deliverable was we developed some model that would be able to predict the availability at each dock station, and then from that availability, we developed an algorithm to sort of rebalance the bikes. The whole idea was we wanted to address the rebalancing issue, which is like if you go to a city bike dock, you don't want it to be completely empty,
right?
From it, and you don't want it to be completely full because then you can't put into it. So ideally, you have somewhere in the middle, some happy medium. So our project really revolves around trying to find a way to mitigate, keep things balanced.
Right. Okay. Yeah, that was cool. Yeah.
But it was good.
Yeah.
All right. So if you want, you're welcome to follow the Dropbox link. The notebook I made for this week is titled Code Challenge 3/29/22.
Yes, actually, I just downloaded it.
Yeah, you can just download it and then open up a Jupyter notebook environment.
So actually, I'm in a different desktop now, and then it's not mine. So I had to go different desktop to open this Jupyter notebook.
Oh no, that's fine. I have a notebook over here. It's just a bunch of links to problems, so I can just send the links in the chat.
Okay. All right. Okay.
You don't need a Jupyter. Yeah, you don't need to. It's just a bunch of links. So we're going to do some Python SQL, and the idea of this notebook was we're going to do a bunch of problems. They're called sort of the class of problems like 2-pointer problems where you sort of have an array of items and you need to do something or find something from the array, and you do it 2 pointers. You track of the left side and the right side, and I'm gonna put the first problem in the chat.
Oh.
And I mean, the hint is that, you can solve it using, I think it's called either 2 pointers, or there's like this shifting, another term is like called shifting windows, because you have this window over the array that you're looking at, which is the 2 pointers. So the way I usually do these is, we'll go over the problem statement, then you can work in it for like 15-20 minutes, then we like regroup and we talk about the solution, or like, what people thought or their approach. But I mean, since it's just me and you, like I said, like we can do it
Right. Yeah.
however you
I
want to do it. We don't even need to do this problems you don't want to do it. If there's different problems you want to do, that's fine.
Okay.
So I'm giving an answer. Oh, sorry.
No. Yeah, I wasn't sure how this meeting would look like, so I wasn't prepared. I'm not prepared for do code challenge actually, but I can try actually. I don't know.
Okay. I mean, but if you're not prepared to do a code challenge, is there anything you do want to do? Like, do you want to talk about like what it was like for job search? I mean, it's just me and you, so we can really do whatever.
Yeah.
Stuff like that.
So no, I don't have anything yet, so I can go over this. So you said 15 minutes?
Yeah.
Okay.
But like I said, if you're not prepared to do it or whatever, like I said, like it's just me and you, so we can do whatever. So yeah, I guess we'll meet back at like 7:25.
Okay. Yep.
If you have any questions or anything, just speak up or put in the chat.
Okay.
Talk about it.
Oh, yeah. Sounds good. Yeah.
Right.
Yeah. Bye. Quick question.
Yep.
Yeah. So do you want me to write a real actual code or just like pseudo code, like some ideas or?
Whatever you can do. I mean, you
Okay.
have environment here in LeetCode, you can like write out the actual code and run it and make sure, see if it works and pass all test cases. Or if not, you can also just like think of an algorithm, a way to approach it, and then we can like actually, we'll look through the pseudocode and then we can actually write the actual code out.
Yeah, I think maybe then that's better since so
Sure.
yeah. So for the water container example, right? Yeah. Container with most water. So what I would like to do is so using for loop, and then from the first line first, what should I say? First column. Yeah, first column to the last column. Like, so basically calculate all the possibility and then return the most case. That's the first thing I could think. And then I'm not sure if the most efficient things though.
Wait, so it was let me just make sure I understand. It's a double for loop.
So yeah, probably. So cause for I to the first for 0 to the length of the each column, and then each. No, so there's only one for loop, I think. So wait, no, one second. Yes, double for loop, because yeah.
Because you want to look at every single pair of endpoints, right?
Right. Yeah. Double for loop.
Yeah. So let me share my screen. I actually didn't think. I'm still doing the problem, but let's do that approach for now. So that wait, let me share my screen. Share screen. So your idea was we want to do a double for loop. We just look at every single pair and just calculate the amount of water that could be between that pair. And just keep track of it. Right?
Yeah, but if it's larger data set, it's not possible pretty much, or it will be really long. So I know it's not a best one, but that's the first thing popped up in my head. So
that's fine. I mean, yeah, but we can still code it out and just see it fail. But yeah, you're right. That's an inefficient solution. But we just code it through. So the idea, and hopefully maybe by coding through this example, we can maybe get a better idea of how to code out the optimal example or the optimal solution. So the idea is we start out, well, we want to find some max capacity, right? We're just
right.
0. And what we're going to do is going to say for I in range length of height.
Yes.
And then for j in range, we'll go from I to length of height. Right. This should give us every single pair.
Right. Yeah.
Such that I is always before j.
Yes.
Right?
Correct.
And then what we want to do is we want to say, so the width, the width of the base, the base length. So base is just going to be equal to j minus I. And then the height is going to be equal to
max of those two heights. Yeah.
Yeah. Height.
No, minimum. I'm sorry.
Yeah. Exactly. Yeah. You're right. Min of height of I, then height of j.
Right.
And then we'll just say like the area is just equal to
that. Well, yeah. Times. Yeah.
Height. All right, and then all we want to do is just say, what we want to do is just see if the area we found is bigger than, let's just call it.
Yeah, so saving, So if area is larger than max capacity, then change it to.
Yeah, exactly. But we can do it, we'll just do it like in one quick liner, but like that's exactly the right logic. We'll just say max capacity is just equal to the max of max capacity.
Oh, yeah. That's
just doing exactly what you're saying. Like, if the value is larger, we define it, else just leave it. This is just a nice, quicker way of doing that. Yeah.
Right. Yeah, it is cool. Yeah.
And at the end, or like you said, like we look through every single pair of endpoints, we calculate the possible capacity. And at the end, we just want to return the max capacity, right? Return max cap. And there's nothing wrong with this. This should work. Base is not defined. Did you mean?
Oh, equal, yeah.
Int object is not subscriptable. Int object not subscriptable. In line 8. That's weird. There's no issue because I and J are both
in the range.
Yeah, and it's just
so
this is an issue with it says a lot of
so it's not int but float. The height will be I don't know, maybe not.
No, I think it says they're all ints, right?
It's that's int. Yeah,
like an issue with like floats or something. I wonder if it's like a problem with like on their end because I and J are both just integers, right? There's nothing weird going on. Height is equal to height of I, height of J. Let's go to discussion, see if there's anything. What was it? The issue? It was something about subscriptable. Well, when in doubt, we'll just take this.
Just, yeah.
Of course, path. Oh, here, let's see if we can't debug. Here, we'll say that, and we will. How do I debug? Oh, there we go. Debug. Okay. Okay, so base is equal to 0. Height is equal to 1. Capacity equals base times height. Sure. Mass capacity is max mass. Sure. Sure.
Oh.
We're not reassigning J anywhere. What?
Yeah, base equals 1, but then height.
Height. Oh, I named this thing height, but we have a list called height. So I see.
I see.
It should be a list. Oh, okay. Oh my gosh. So let's just say
Just
H
H,
for height.
yeah, okay.
Gosh. All right. So now we run the code. Okay.
Right.
Okay. So this works. Okay. Cool.
So the output, yeah, okay. Yeah.
Just commit it. We should. I mean, we're not gonna get accepted, but because it's gonna be, it should be a time limit exceeded error. But that's fine. It means that our algorithm works, but we need to think about it a little bit more. Yeah, it's taking this long. Yeah, time limit exceeded on some.
Yeah.
It was O of n squared. There is an O of n way with using 2 pointers. So I'm just gonna set it up real quick, and I'm gonna talk through it as I code it up. So this was our O of n solution, which is fine. Well, it's not fine. I mean, we're gonna get it.
Yeah.
So I'm just gonna say, just store some values. I'm gonna say n is gonna be the length of height. And so the idea with the 2 pointers is what we're gonna do is we're gonna start one pointer over here and one pointer on the other side. And we're gonna calculate the capacity of where those 2 pointers are. So when left starts over here and right starts over here, we calculate the base like we did before, and we calculate the height based off the minimum of the 2, and then we calculate that area.
Right.
And we store that area. We see if it's greater than our max area. But then the trick is, so we have a pointer over here and a pointer over here. We're going to increment the smaller height, right? Because we want to find the largest area. We don't want to get rid of something that's taller. We only want to increment over. We want to get rid of a smaller height, right? So in this case over here, we have left is equal to 0 and right is equal to over here. When we calculate this area, which looks like it's going to be maybe 9, however long this array is. When we want to look at our next wall, we want to consider. We don't want to not consider this guy because it's already pretty tall. We want to not consider the shortest guy, right? So we increment this guy over, right? So that's the idea, is like that. So the way with left-right pointer algorithms works, we always need to initialize these pointers. Hello, Hugh. Is that Hugh?
What's up, Charles?
Hey, how's it going, Hugh? Let me share the notebook real quick. Actually, I'll just share the link. It might be a little in the chat, and I'll share the notebook once I do this. So we have this, and he's like, and we're gonna have these 2 pointers. We're gonna say left is equal to, I'll do left, right is equal to 0 and n minus 1, right? So I was gonna set our left pointers to the beginning of the array and the end of the array, right?
Mm-hmm.
And the way this is going to work is we're going to keep on doing this process where we try to calculate the new area until our left pointer is equal to our right pointer, until they meet. So I'm going to say while left is less than r, what am I going to do? Well, we're going to do the same thing we did before, right? We want to first find the height, which is just going to be the minimum of the two, right? So I'm going to say, I'm going to make a mistake. I'll say h is equal to min of height of our left pointer and height of our right pointer. So for the example over here, our min is going to be obviously this 1 value over here. And then we want to do the same thing. We want to calculate the base, right? So our base is equal to what?
So r minus l.
Yeah, exactly. That's just our base. Just like in our example before, except we had j minus I, but the exact same, right? So then we know our area. Oh, sorry. Just like before, you know, what we're trying to track is our max area. I just didn't make that variable. We'll set that to 0 because we haven't seen anything at that point. We say our area, and we'll do the same thing before. We'll say area is just equal to base times height. And then we'll just say our largest area or max area. We'll do the exact same thing before as is this the max of max area and area. Right? So we start out our left and right pointers over here and here. We just calculate the base and the height as we did before, see how much more we can calculate. And then we just see is this max area we found bigger than our previous max area, right? And we just store it. So now the trick is we need to figure out, you know, how do we increment our pointers, right? We said before, when we have 2 pointers, like here we have a pointer at 0 and a pointer over here. We want to increment we want to move the smaller one, right? Because we don't want to move the bigger one because that can only result, we don't want to move the bigger one because that might result in a smaller value. But if we move the smaller one, that could result in a larger area.
Right? Makes sense. Yeah.
So we want to say, we'll say if height of L is less than height of R, then what are we going to do?
And L equals L plus 1.
Yeah, exactly. L, we're going to increment our left pointer.
Right, yeah.
Say else
R minus equals to 1, yeah.
Exactly. And you can see how this will eventually terminate, right? Because we have this while L is less than R, we're going to keep on doing this thing where we calculate the height, the base, calculate the area. And then we always, in our loop, we always decrement or increment a pointer so they will eventually meet and the code will eventually terminate. It's not going to run forever. Which is something you need to be a little aware of when you're doing these like double pointers. You need to make sure the code actually terminates or, you know, finishes. Okay, so that's it. Is we have this code. So what's going to happen over here is, you know, we start with 0 and over here we do our first calculation. We get some number. Okay. And then we check the heights. When we get, since height of L is less than R, we know left goes over here. And then we do our new calculation. We look, well, we calculate our new area, which is going to be some much larger area, obviously. We store it. It's going to overwrite the value of max area. And at this point, since L is here and R is here, we're going to increment the smaller value, which is actually going to be R. So R is going to move over to here. And then it's going on and on and on until they meet in the middle, and we find our max area. So at the end, we've done this area. All we got to do is just return our max area. And hopefully, as long as I didn't do anything weird.
I think there's 2 8s for the height numbers. So I think you should think about when the column heights are same each other.
That's a good point. That's good. So when they're the same, it's like a toss-up, right?
Yeah.
I think so. If we run our code now, because you might be right. It may be something we need to consider. But I think okay, so it did pass, but if I go back here, it passed because, well, if they're the same, then we can move either one, right? Because either one potentially would give us
Yeah.
better answer. The only issue was if one was shorter than the other, then we don't want to move the bigger one because we're just shooting ourselves in the foot, right? Because we potentially could have gotten rid of the bigger area. So when they're equal, it's just like, whatever. You can increment either. I could have said over here less than or equal to, so that when they're equal, you increment L. Without that, R gets incremented.
Oh, yeah, I see. Okay, yeah.
Either way, the code still runs.
I see it now. Yeah, I understand. Yep, makes sense.
So yeah. So Hugh, you joined a little late. So what we did was we looked at this problem, which was like a max pointer problem, and we had an initial solution. Our initial idea was we want to look at every single start and endpoint, calculate the area, or sorry, the amount of water that could possibly populate that area, and then record the max capacity we find. The issue with that was it was a double for loop, so it was O of n squared. And when we went to our submissions, we see our first submission was
time limit. Yeah,
we got TLE, a time limit exceeded error. So then we had to think a little bit more about how to do this like linearly, and we have this double pointer solution, and this is an O of n solution because we're only iterating to the array once, or sorry, iterating to the array once. So it's O of n, and we managed to get it to be below the time limit. So are there any questions about this problem?
I'm good. Yeah.
All right, cool. I can share the notebook link if you want. Yeah. Let me just find that real quick for you. Chat. Oh wait, that wasn't it. That was the sorry. Wait. There we go. That should hopefully be it. All right, and I'll copy over the second problem. Another leak code problem. I'll copy it over to the chat so Jungle, you can see it.
Thanks. Yeah.
All right, I'll just give Hugh a minute to open up whatever notebook or anything he needs to open up.
Do I need the notebook, or are we just doing leak code problems?
No. I'm just I put the leak code problem in the chat because Jungwoo can't open up. He's not on like a home computer, but it's just a bunch of leak code links. So yeah, you don't need the notebook.
Okay.
Yeah, you can just follow the links in the chat. All right. So the second problem we're gonna do is a problem called Coco eating bananas. So if we open it, I am sharing my screen. All right, we'll just go through the problem statement. So we said, Coco loves to eat bananas. There are n piles of bananas. The ith pile has piles of I bananas. The guards have gone and will come back in H hours. Coco can decide her bananas per hour eating speed of K. Each hour, she chooses some pile of bananas and eats K bananas from that pile. The pile has less than K bananas. She eats all of them instead and will not eat any more bananas during this hour. Coco likes to eat slowly, but still wants to finish eating all the bananas before the guards return. Return the minimum integer K such that she can eat all the bananas within H hours. All right, so we got a bunch of piles of bananas, and this is give you a hint, it's a binary search problem, right? Is we're trying to find some minimum value. And binary search is like it's a double pointer problem. We always have a left and a right pointer, and we, move those accordingly to some condition. So binary search is certainly a double pointer type problem. So you have all these piles of bananas. We need to find we want to find the minimum value such that she can finish the minimum rate at which she eats bananas so that she can finish them within 8 hours. So we have some absolute low rate, which is, she can't eat them any faster than 0 hours. And the maximum rate of bananas, you have to figure out what that maximum should be. And then you have a left and a right value. And then from there, you can do binary search. I'm not sure that was any clearer, but if anyone has any question on the prompt statement, feel free to speak up. I think we'll meet back at 7:50 to discuss our solutions or partial solutions or pseudocode or whatever we've come up with. And again, if there's any questions in the meantime, feel free to speak up in the chat or message me. All right. I think we'll reconvene. Anyone want to share any ideas or pseudocode or thought process for how to go about this problem?
Yeah, actually, so what I was doing, so I didn't finish it actually, but what I was doing was choose the maximum piles as a speed for the first, and then divide it by for each piles, and then add the round up times, and then see if it's less than the h value, and if it's less than h, then go to the next highest piles, and then repeat it again and until the total times equals h or over than h. So in that
Okay, yeah.
wise, yeah.
Okay, so I see what you're doing. So we have you're saying so okay. So for well, you have like some I equals 1. Or let's say rate, we'll start with rate equals 1, right?
Right.
Say while whatever. We're gonna keep on doing this. Okay, yeah. So I'll say if we have like some can, imagine some like can finish function that takes the rate. You know, we're saying if I can finish at this rate, then just return rate.
The rate.
Else I'm just gonna make rate plus equal 1.
Yep.
And then so that's return it, yeah. So we start off. Okay, so this is a linear search, right? So we start off at the smallest value we can, and we just see if we can finish at this rate, then return that rate because we know it's the smallest possible value, right? The only thing we need to write here is this can finish function. So can finish. Can finish.
Rate or yeah.
Yeah, it takes a rate. So we want to say, let's say, we'll have some value num hours is gonna be the number of hours it takes to finish. And we'll say for pile in piles, I'll say num hours plus equals
then piles divided by maximum piles. No, that doesn't make. I mean,
close.
So yeah.
Pile divided by rate, right? Because if we have like 4 bananas in our pile and our rate is 1, then we want to do 4 divided by 1 to find out the number.
Right. Yes. Correct. Yeah.
But there's a little trick to this is we want to right. It says in the problem is Coco isn't going to eat a fraction of a banana.
So
yeah. Yeah, it says each hour she chooses some pile of bananas, eats k bananas from that pile. Yeah, k, some integer k value, right? So we need to, in case this is a ceiling, we're going to say she's not going to eat 4.8 bananas. She's going to eat 5 bananas, right?
Right. Yep.
Or
so it's round up. Yep. Say yeah.
Yeah. So we just round it up to get the number of hours, right? So we say number of hours equal for pile and piles. We'll say the number of hours plus equals math.ceiling, and then we say if num hours is greater than h.
Yep.
What do you want to return?
Then
imagine it's like returns a boolean. Like what? Then what's like
the rate plus 1? Oh no, the next then.
All we want to return is this can finish is going to return a true or false.
Oh yeah.
So if num hours is greater than h, then we know that we've already spent more time than allocated, so we know that we can't finish, right? So we're just going to return false.
I got you. Yeah.
Yeah. And then otherwise we're just going to return true, right? We get through every single pile. We've never hit this terminating condition. So we're going to just hit this one. This should be a decent,
Yeah.
right?
Mm-hmm.
Just to make sure a sanity check, we start out with 0, and for every pile, we calculate how many hours it would take to finish that pile.
Mm-hmm.
And we say if num hours is greater than the number of hours we have allocated, we can't finish, we return false. Otherwise, we keep on continuing. If we can get through every single pile without ever going over the allotted number of hours, we just return true.
Yep.
All right, so this hopefully, so this is going to be, all right, this runs. Let's see. Hopefully we get a time limit exceeded error. It means our logic is correct, it's just too slow of a function.
So yeah, I was, time limits, of course.
Yeah.
So the rate should be not just by +1, but yeah, moving a little bit bigger, like you said, from double points. Yeah,
exactly. So we have like a linear search, like we just go through everything and we eventually will find the value that we want. That's O of n. But like I said, we can use binary search, and that will be log n, right, to find something. Right. So for this, what we have right here is we have this while true loop is going to be like an O of n like thing, but inside of this while loop, we have this if can finish, right? And this if can finish is an O of n operation. We need to iterate through the whole array. Iterate through the whole array every time and calculate to see if we can finish. So that's O of n within an O of n. So that's going to be O of n squared, right? So if we can somehow reduce this second here to be log n with binary search, then our time complexity is going to reduce from O of n squared to O of n log n, which is going to be much faster. So we have our can finish function is actually, we can just use that over for the binary search. So all we got to do is the binary search, right? So for binary search, we need a lower bound and an upper bound to consider, right? So let's say, we'll comment this out. Let's just say this was O n squared, all right? We're gonna, down here, we're gonna do a binary search. So first thing for binary search, we need a left and a right value. So what would those be? Remember, our left and right values here are gonna, what we're trying to find is the rate. So our left is our least rate, and our R is the biggest rate we'll consider. So what should those values be?
So the minimum and maximum of piles each? No.
Certainly. Yeah. No, yeah. I think in my code, I actually have my lower is 1, because I just started at 1, but you're right. Yeah, the minimum we should start at is the minimum of the piles, right? Because there's no reason to consider anything less. We know that we can do it quicker.
Yeah, because it was same time consuming, or
Yeah, no, that's I actually didn't test that. I had 1 because that's minimum like terminate. So yeah, let's just say min of piles, and then our max, we're gonna say max of piles, right? Because So okay, good. So we have our left, our upper. So we have our lower rate and we have our upper rate. And now we just do a standard binary search. We just want to say, we'll say while L is less than or equal to R. So while L is less than or equal to R, excuse me, what we're going to do with binary search is we have an L and an R value. We want to calculate the midpoint, right? That's what binary search does. So we're going to say mid is going to be equal to, well, the mid between L and R is just going to be L plus R. I'll do floor because we want the point to be an integer, not a float value.
Right.
We can actually index the array. And then what do we want to say? We have this mid value, right? We want to see if given this mid value, and mid represents a rate, right? We want to test to see if we can finish given this mid value.
Yeah.
So all we're going to say is, what?
No, and then just following you. Yeah.
Oh, yeah, okay. So we'll just say, if we can finish, what did I call it? Can underscore finish. If can finish at this mid rate, then that means, then which pointer do we want to update?
1 second. If it's true, then
So if this is true, we can finish at this rate, then we know, okay, fine, we can finish at this rate, but if we can finish at this rate, potentially we may be able to finish at a smaller rate, right?
Yeah.
We don't want to consider any rates larger. Or
Right.
sorry.
So,
We want to consider larger rates, right?
yeah. I mean, minimum of larger rate. I mean, yes, I think. Yeah.
So we're going to say, wait, let me sure, right? Mid. Right. If can finish this rate, we say our right value. Oh, sorry. Yeah. Okay. I had the question backwards. Yeah. We want to find the minimum rate, right? So if we can finish at this rate, then we know we don't need to consider any larger rates, right?
Yeah.
Exactly. So we're going to move our right pointer to the mid value, and that's going to cut off our search by half, right? At the beginning. Right. Because that's what binary search does. We have all these values, and if we can,
chunk, yeah.
Yeah. If we can finish, then we want to set our right pointer to be the mid value. Else we'll set our left pointer to be just equal to the mid value plus 1, right? Because if we can't finish at this rate, then we need to consider bigger values, right? So we need to consider everything to the left. We want to consider everything to the left of the mid value. Sorry, we want to consider everything to the right of the mid value.
Yeah. I got you.
Okay. Yeah. Sorry. Again.
Yeah.
So we start out with min and max of the piles, and say while we haven't converged on some value, we calculate the midpoint. If we can finish at this midpoint, then we know we can finish at a lower rate, so we constrain our search to the lower rates by setting R equal to the midpoint. If we can't finish, then we need to consider higher rates, and we constrain our search by setting L equal to the midpoint. So we look at the upper range of values.
Right. Yeah.
Upper range values. And then this is gonna keep on going and going until it converges on some midpoint. Once L is less than R, then all we gotta do is just return. We want to return. What do we want to return? Either we want to return L, right? We want to return the smaller of the two values.
Yes.
Yeah, they're both. Yeah. I think either would be fine, but yeah, L would certainly work. All right. Yeah. So this is our binary search. It's like sort of a. Binary search is like pretty boilerplate, actually. A lot of the times it's just this same setup. You have your left and right. This is always the same while left R.
Yeah.
You calculate your midpoint. This is always the same. The only thing that changes is your condition, whatever condition you're trying to test. This is something that can change, but you always some Boolean value. If this is met, you set some pointer. If the condition is not met, you set some other pointer, and you continue on and return L. So hopefully now we have no issues. I should be able to run this. Name rate is not defined. Oh, mid.
No, yeah. Right.
Yeah. The middle, yes, the middle value rate. Okay, so run code. All right, passes for that. Wrong answer.
Wrong answer.
Uh-oh. So okay, so we can't, if you consider this, the min value would be 31, 28, 40, whatever, right? And the max value would also be 21, 48, whatever, right? So those are already equal. Right? So I'm going to do, so what it's returning is, oh, okay. So I think what happens, so since they're equal, so while they're equal now, right? So this is going to happen once. So the mid value is just going to be equal to 312884470, right? Because I'm just taking that number, adding it to itself, and dividing by 2. So if I can finish at this rate, which I can, if I can finish at this rate, then I'm just say R is going to be equal to 31, this whole number minus 1. And then, so now I have L is equal to, whatever, this big number, 470. I have R is equal to this whole number minus it. So when I go to the while loop again, this condition is going to not be satisfied, so it's automatically going to return L, which is still the initial value. So I think what we actually do, so you see the issue is we don't want to consider min. Well, I thought that was like, a clever way to sort of cut our search down. I think we want to consider 1.
1. Okay. Yeah.
That's our theoretical minimum. So if we run this code, hopefully, all right. Oh, voila. Okay. Now I thought that might have worked actually, but yeah, now looking at it, yes. Yeah.
From 1.
1 is our theoretical minimum. Yeah.
Gotcha. Oh, yeah.
Yeah. So this is so just to reiterate again, we just have this helper function that just it's an O of n. It just goes through the piles array and calculates whether or not given some rate we can finish all the piles within our time constraint h. And then our initial solution was okay. All we do is start from 1, and just every time we set our rate to 1, and we just while we can finish, if we can finish, then we return. So while true, if we can finish, then we just return that rate. Else, we just check the next rate and keep on going to the end. Linear search, so that's O of n, but inside that linear search, we're also doing an O of n operation. So that overall is an O of n squared operation. So we said we can do better. Instead of doing linear search, we do binary search. Binary search is log n, but since our if can finish is an O of n operation, we're doing that within this log n loop. Our overall time complexity is going to be n log n here. And we passed the test case and everything. So are there any questions on this question or binary search or anything?
No, for me it's good. It looks good.
Okay. All right. Well, I think we'll just take a 5-minute break, and then we're gonna continue on for the next one.
Okay.
I'm gonna grab some water. I had to need some water, but we'll be back at 8:12.
Sounds good.
All right, welcome back. So we got one more Python problem. I want to do copy. I'll send it out in chat. Again, two-pointer problem. I will do solutions. All right. So it was called max consecutive ones 3. So given a binary array num and an integer k, return the maximum number of consecutive ones in the array if you can flip at most k zeros. So for example, down here, we have this nums array and we have 2 flips. So we can change 2 zeros to ones, and we want to say, given this, what's the longest sequence we can make? So the output is 6, and that's because if we flip these 2, then the sequence we get here is of length 6. I mean, alternatively, you can consider if you flip these 2 zeros, the one trailing and the one leading, you'd also get a sequence of length 6. The reason is this one is because if you flip these 2, that's only 5. So the reason it's 6 because over here you have, this sequence or this sequence that produces the longest continuous sequence of ones. Down here we have this nums array as well, and here we have 3 flips. So the output is 10 because it looks like over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Or maybe it's 2. Oh, okay. The expression is down here. It's 10 because you can flip 1, 2, and then you have these 3 ones, and then you can flip the third one, and then you can add these 2 on, and you get this sequence of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, that's 10. So yeah, this is 10 because you can flip these 2, and you can flip this third one. So once again, this is a 2-pointer problem. I think this one's a little trickier, so I want to give it a little longer. I think we'll reconvene at 8:30 to discuss any solutions or partial solutions or algorithms or pseudocode to approach the problem. But again, until then, if you have any questions about the problem or want to share any ideas, just speak up in the chat or speak up just vocally. All right, until 8:30, that's when we'll reconvene to discuss the solution. All right, welcome back, everyone. Share my screen. All right. Does anyone have any ideas or code they want to share on how to approach this problem?
No luck for me. I was trying to use some, I don't know, index, but no, I mean, yeah, I don't have any, yeah.
It is certainly a tricky problem. But if there's no idea, then I think what I want to lay out the algorithm is like this: is like you almost imagine it as like over here. You imagine like each one is like a tile that you can walk on, and each zero is like you can't walk there, and you have k tiles that you can put down. So if like here like k is equal to 2, then what I'm going to do is I walk, and I see a 0. So what I do is I put down a tile, aka turn this to a 1, and then now k is equal to 1. And then I walk again, I put down another tile. Now k is equal to 0. But now, whatever, I don't know what I'm doing there. But now I'm at a 0, and I have no more tiles to put down. So to continue on, I gotta pick up the first tile I put down and put it down in front of me, right? So I gotta turn that to a 0, make that a 1, and then I can continue on. I see a 1, I don't need to put a tile down. So I go on until I hit 0 again, but I have no more tiles to put down. So I gotta pick up the last tile I put down. Sorry, the first tile I put down, pick it up and put it down over here. Oh, and then I get my sequence of 1s, right? So that's sort of, it's not exactly how it's going to work out, but that's very, very similar close. It's like I'm trying to walk as far as I can. I hit a point where I can't walk. I put a tile down. I keep on doing that until I have no more tiles. And if I still have potential places to walk, then to walk to the next spot, I got to pick up where I came from before and put it down in front of me. And we'll continue on and on like that. So I think we're just going to walk through the code, and hopefully that'll like sort of like materialize the algorithm more as we walk through the code. So as with all double pointer sliding window algorithms, we have a left and a right pointer, which will initialize. Well, L equals R is equal to, and we also actually have, what do we want to keep track of? We want to keep track of the max length. So I'll just say like max length, and we're going to initialize all these to 0. So that's what's different about this left-right pointer. Our problem is like our left and our right pointer both start on the same side of the array in this one, whereas in the previous 2 examples we saw they start on opposite sides of the array. So again, for the example over here, we have our left and right pointer are both over here. So what I'm going to do is I'm going to say, okay, I can take a step, right? And then what I'm going to do is I'm going to say, so the max length I've seen so far is equal to my right pointer minus my left, right? Since I can take a step, I update my right, which is now 1, my left is 0, and I'm going to take the difference. That's the length. And that's sort of why we're starting on the same side, because what we're going to do is we're going to walk and walk and walk. We'll put down a tile here because k equals 2, right? Magic k equals 2. We'll put down, I got to make this a 0. Which is a 0, it doesn't matter. And we walk, and we put down another tile. And every time we take a step, we want to see where we came from, like where we started from. So we subtract the 2 indices to get sort of the length, right?
Yeah.
And we're gonna, so that's why we're starting on the same side. We start max length is equal to 0, right? And what we're gonna do is we're gonna do this. So while r is less than length of nums, we're gonna say while there's still places to walk, while there's still like an array to continue.
It's the wall, yeah.
Yeah, we're gonna consider this procedure. One more thing. So we have an example over here. Maybe I do some less. Try to do a small one. One. And again, we say k equals 2. Let me put a 0 here. 1. Yeah. So we have k equals 2. We said before that what we want to do is we want to pick up. So we have a 0 here. So I'm going to put down a tile. We'll say k equals 1 actually for this case. So for this example, we start left and right equals 0. we have one tile to put down, right? So we start here, we can't walk anywhere, so we need to put that tile down. So we put this tile down, right? Let's say k equals 2. Sorry. Put this tile down. All right. But now, remember I said, like, we're going to keep on doing this. We go over, okay, 1 we can walk, 1 we can walk. 0, okay, put a tile down. So now we have 0 tiles. We put down 2 tiles, right?
Yep.
But now we're going to keep on continue on, right? So what I need to do is I need to pick up the earliest tile I put down, right? I need to take this tile I put down here. I need to move it over here. So what I need to remember and keep track of is the index of where I'm flipping or where I'm putting these tiles down, right? Because I need that to know where to pick up the previous tile and put it down in front of me. So I'm going to have a list. I'm going to call it zeros. And it's going to be, a deck. A deck is a double-sided cube. What's important for this is that what it allows me to do is it allows me to pull from the front of this list in O of 1 time. Right? With an array, if I want to remove an element from the list, it's O of n, because I got to remove the element and then I got to move everything over. With a deck, which acts very similarly to a list, it allows me to remove the first element in O of 1 time. So you can think of it as just like it's a queue where I can remove the first element in O of 1 time. So while R is less than length, what do I want to say? Well, the first thing I'm going to do is I'm going to say, well, if it's a spot I can't move, so I'm going to say if nums of 0, or sorry, nums of R is equal to 0. So if nums of R is equal to 0, and I'm going to say this, and length of zeros is less than k. What does that mean? What does that like physically
The
mean?
number of tiles left.
Yeah, it literally means I still have tiles to put down, right? It means I hit a spot I can't walk on, but I still have like a tile to put down. So I'm gonna say if nums of R is equal to 0 and length of 0 is less than k, then what am I going to do? What I'm going to do is I'm going to put down a tile. So the act of putting down a tile is what I'm going to do is I'm just going to put that index onto my queue, onto my deck, into the zeros thing. So what I'm going to say is I'm going to say zeros dot append, right? So if we hit a spot that we can't walk on, a 0 spot, and I still have tiles that I can put down, then I'm going to put down a tile, right? So I'm going to append R, right? And this automatically keeps track of how many tiles we have left, because we know that if length of zeros hits to k, we put all of our tiles down. We know we can't put a tile down. And if it's less than k, then we still know we have tiles. So we don't need to keep track of, we don't need to like increment or decrement k. That information is sort of kept indirectly in the length of our queue, because our queue represents where we put a tile down, or the indices of where we put a tile down. So just the number of indices is just the number of tiles we put down. So 0 dot append R. What I'm going to say is else if, I'm going to say else if nums of R, let's say nums of R is equal to, it's another spot we can't walk, and length of zeros is equal to k, meaning we put down all of our tiles. We have, if we have k equals 4 and our zeros is length 4, we have 4 tiles down some indices. So what this is saying is if nums of R is equal to 0 and length of 0 is equal to k, as in we have a spot we can walk on, but we've already used all of our tiles. What I'm going to do is I want to pick up the first tile I put down, right?
Yeah.
The first tile I put down is the 0th index of the zeros, right?
Oh yeah, it's the zeros. Yeah.
Because I always append, whenever I hit a spot that I can't walk on and I have tiles, I append to the end of the list. So the beginning of the list is the first tile I put down.
Yeah.
So I'm going to pick up the first tile I put down, I'm going to put it in front of me essentially. So what I'm going to do, I'm going to say, well, first of all, I'll say,
So like drop the first one and then append the last one.
Yeah, exactly. So I'll append. Actually, it's in the other order, but the code I wrote is like this. So I'll say I'm going to append, this index I'm at, but then I got to remove. I'm going to put another tile down. It's got to come from somewhere, right? So then I got to do exactly what you said. I got to say zeros dot, and the function here is pop left. And what that's going to do is going to pop the first element. It's going to pop from the left side. It's taking that element and removing it and returning it to me. So I'm going to say my left index is going to be equal to zeros dot pop left little tricky here, +1. And we'll see in a little bit why this is +1. So just to iterate over again, we say, you know, if we're at a spot we can't walk on and we have tiles left, we're just going to pen that tile onto our zeros. We're gonna keep track of where we put it down. You know, if nums of r, if we hit a spot we can't walk on and we still have tiles to put down, we're going to walk onto the spot, but we're going to replace it. We're going to replace that spot with a tile from prior. So we're going to move forward, but we got to take the first index we put it and first index of the tile, the index of the first tile we placed, and remove it. And we're going to store into L.
Yeah,
You can see why.
makes sense.
So-
yeah.
Okay, cool. And then what we're going to do is we put the tile down, and then we're going to increment our R. We're going to move forward onto that value, R plus equals 1. And now I'm going to say max length is going to be equal to max of max length or R minus L. Right? So if we look at
yes.
yeah, so if we look at this example here, I think it started, yeah, so if it's 2, let's say we got, let's say like this. We can't walk, so we put a tile down. Put a tile down. How do I, maybe I'll do it over here actually so that we can stay in the window of the code. So I've got, well, let's just do this one. So we start here, or I say if we can walk, if we can't walk, which we can, so we don't even hit any of these any of these cases, I just increment R up 1, right? And then I just want to say the max length is equal to the max length we've seen so far, the max of the max length we've seen so far, or R minus L. Right now, R is 1 and L is 0. So we take that, we get the max is 0 and 1. So the max passed so far is 1, right? Then we go again. We say, well, if this thing is 0, it's not. So all we do is increment R by 1 again and take 2 minus 0. All right. We go through again, we increment, we see that we once again, so we're here. Now we're here. Here, we say, well, nums of R is not equal to 0. So I increment R and I take the difference. So now 0, so now R is here. I take the difference from R and L. So it's these 3, right? All right. So now where it gets interesting. Now R is equal, nums of R is equal to 0 at this point. We're here. And we haven't used any tiles, right? So what we do is we zeros is out just equal to 3. We're gonna keep track of this index. We put a tile down here, right? It's like we turn this to 1. And we store that value. It's the same thing as like sort of setting it to 1, but we don't do it in the code, so I won't do that here. And then all I do is I increment R by 1. And I take the difference. So now L is 0, R is 4. So I get 4 minus 0, I get 4, right? Because we put this tile down like that. And so we have a length of 4. So now we have 1 tile left, let's say. We are, R again is 0, so we append the next tile is 4. You know, so we put this tile down here. Then I increment R. Increment R, and then I just see the difference. So now it's 5, right? 5 is the best. Okay, next iteration. We now have this case here where our length is 0, and now we've put down as many tiles as we have. So what we have to do is, I have a 0 here, right? So I'm going to append this value, 5.
Yeah.
But then I got to pop this third value off, right? So that's here, 0, 1, 2, 3. So what I do is I uncomment. I pop that guy off. It's now not walkable, right? So now I set that value equal to L plus 1. So now L is equal to 4 at this point. So now since R is equal to 5 and L is equal to 4, I get the difference of 1, right?
Yep.
And that's this length here. And that's why we need to store the zeros indexed in the L value and update L accordingly according to the 0.
Right.
And so we can like sort of track, we go as far as we possibly can. And when we had to take a value off, we know we're breaking the continuity. So we reset our L index to where we broke the continuity. So we can continue tracking the length there. Does all make sense?
Yeah.
Okay. I just want to make sure
So
that the reason we were like storing the index of the last 0 plus 1 to the L was clear.
Yeah, but the actual norms list has just one, right? It's not changing. I mean, you don't. I mean, never mind. You didn't change it. So, and never mind. Yeah, I'm good.
Okay. All right. Because yeah. So this whole process continues where we update the R value, and then once we run out of tiles to put down, that's when we update the left value, right? We've broken continuity from placing down tiles. So to recalculate the longest continuous subsequence, we only want to consider from the point where we put down the first tile up to our current point, which is why we set L equals to 0 dot pop left plus 1. So we can do this all over, and all we do at the end is we just return max length. So hopefully if this runs, I said NAD and. All right, it seems to work. We submit it, and voila, it works. Is there any questions about this? This is quite a tricky problem, I think.
I mean, yeah, I was confused in the beginning, but I mean, it makes sense. Like, yeah. So now, yeah.
Yeah, I think it's easy to think about it as if it's just like tiles. It's like I'm literally just trying to walk. I put a tile down. I have no more tiles. All right, I got to pick up my previous tile, put it down in front of me, and see how long I walked.
Right.
But yeah, all right. If there's no question on this problem, again, these are the 3 double pointer problems. They seem to be asked a lot. From what I've read and from my experience, I was actually asked this very similar question in an interview. Yeah, people seem to love double pointer problems. So they're definitely worth putting some time into it. I'm not sure. It's more of like a software engineer type question than it is like a data science type question. I think I'd maybe be a little surprised they asked this hard of a double pointer problem for a data science interview for the coding part, but definitely it's a topic that you certainly want to look into and like sort of be aware of.
Yeah.
All right. So we'll continue on with our SQL problem. Just copy this link. And this will be our last problem of the night. And just find the chat. All right. And just follow the link. With my code. So have you ever used Strata Scratch before or heard of it?
This one?
Strata Scratch.
No.
But you see the page right now, right?
Yeah.
Okay. So this is just it's like lead code, but for SQL mostly. So you have a problem statement here, and you have the tables involved the problem statement here, and you write your query here to do whatever you need to do, and then down here you can test your query, or you can run it. Your side will say run because I've already solved this problem. So if you write some query like select all from Google Gmail emails. And run it. You can see your output down here if you want to debug, or you can click submit. And obviously this is not the answer to the problem, but this is where you'll see your whether or not you've gotten a question correct. So we'll just run through the problem statement, and then we will do the problem. So this is likely from Google. So we want to find the email activity rank for each user. Email activity rank is defined by the total number of emails sent. The user with the highest number of emails sent will have a rank of 1, and so on. Output the user, total emails, and their activity rank. Order records by the total emails in descending order. Sort users with the same number of emails in alphabetical order. In your rankings, return a unique value, even if multiple users have the same number of emails. So we got some hints down here if you'd like. And again, the relevant table you need is here. So when in your query, this is the table you'll be selecting from. So if there's any questions on the problem statement. All right, if not, I think, let's say we'll come back at 9 o'clock and we'll discuss the solution.
Okay.
It's not horrible, but there is a I'm not sure how hard it will be without this certain function, but there's a function that I found that actually made it relatively straightforward. But yeah, we'll come back at 9 o'clock and we will discuss solutions.
Okay.
All right, welcome back. Anyone want to have a solution they want to share in the chat, or I mean, I already got Hughes, so I'll go through Hughes, but
Let me share my tool, but I mean,
all right. So let's just go through Hughes first. I just have it up. So he says, select from user. We want to select count from. Oh, let me not do this. We want to select the count because we're grouping by from user. We'll select the count, the number of rows in each group, and then we're going to rank over. So we're going to assign a ranking over order by. We want to order by the count in each group, descending over from user as actual rank from Google, Gmail, emails, group by from user, order by act rank.
I don't think you need the last order by act rank. I think it
yeah, I think, yeah, you're right. Because the order by statement, oh gosh. Yeah, the order by, when you use order by, it automatically orders the rows for you. So if we run that code and submit it, that seems right. What's weird about this problem is that nowhere here are we ordering or checking the order by the name, which they said we should use to break ties, and we still pass the test, all the test cases.
well, it's sorting it by from user, I think, alphabetically, but it is weird that it's like not a name, it's a numbers too.
Or, yeah, it's like a number string or whatever. Yeah. It's just a bizarre, like, doesn't really, it asks for you to do that, but then it doesn't like come up as like an issue with the test case. It's bizarre. But all right, yeah. I did like something very, very similar. I just found like a little like built-in function that I'm going to share. But before that, let's look at Django solution. So
definitely, I don't think it's gonna work.
I will say we'll just run it real quick. Syntax error. So let's see, select ID. Let's select count of 2 user.
I think I was confused a little bit. So
That's fine. I mean, is it this as? Let's see what the issue is. We can probably figure out what it. Row number over order by. Oh, see, so this counts doesn't exist yet, right? Because you're defining it here, so you can only use that outside of this query. So we'd have to say like, just that and then put it over here, which is a little annoying. Oh, maybe that. Why do we have so many? Where does this go? That's good. Okay, well that didn't fix it. So what's the issue? Since they're adding your row number, count distinct to user. Why is that?
You're missing a comma.
Oh, that the counts.
Gosh, yeah. Oh my god, yeah. So let me see. Actually, before I do all that, let me actually see. I mean, I think I'm still. Yeah, column counts does not exist, so we'll still have to take this and just throw it on in here. Okay, we get something. Oh, get something very bizarre.
Okay, I think.
Yeah, I'm not sure. So we're selecting ID. Oh, because we don't want the ID. We want the from user or the to user, right?
Yeah.
But we want it to be the from user because we want the people sending the email. So if we from, this may not fix it. Ooh.
I group by ID, so
yeah, so we have to group by from user, and then we might need to also just do count distinct from user. Yeah, so there's some cases failing. I think that's because we're only counting the 2 users. So potentially we just make this from user and make this from user. Oh my gosh, what's the issue? So from user count. Oh, because we don't. So we want to count how many emails are sent. But if we count distinct, then everything's just going to be, I think everything's just going to be 1, right?
So, okay, yeah.
Maybe it's just count star. This is slowly just flowing into.
So yeah, it counts all, yeah, from users, yeah.
That might be the issue. Huh. Wait. There's a solution output. Our solution output. Oh, did we not order by correctly?
I think the row numbers are assigned before the order by. That's the problem.
Sorry, Hugh, what was that?
I think because you're using the row number, like the row number is getting assigned before you're ordering by counts. I think that's the. Oh wait. No.
Get rid of that. Wait. Because it's by default, I think it's ascending, so we want to say descending.
Oh,
Right?
okay.
That I think that was the. Okay, we're still getting some weird
Getting
stuff. But we're getting there. We're getting there. From user count. Sending. Okay. Okay, so I had to add a second argument to over, which from user. Hugh, do you remember what this second argument does?
You're ordering by counts and then you're ordering by from user.
Oh,
So
okay.
if it's a tie, it's breaking the tie with alphabetically.
That's right. It's not a second.
It's numbers, so like.
Yeah, it's not a second argument. It's just ordering by count and then ordering by from user to break ties. Okay, so that makes sense.
Yep.
Okay, my solution is exactly what this solution turned into. I just thought it was cool to use this like row number built-in function. But I mean, it does the exact same thing that Hugh's solution did, where used just order by at the end. This just sort of does that for you. Yeah, this wasn't like a particularly like, I know it's labeled as hard, and that's the thing about Stratus Scratch is sometimes the labels are misleading. But I liked it because you get to use this like sort of new function, which sometimes it's hard to find problems that don't introduce new functions. But yeah, are there any questions on this problem?
No, I'm good.
All right. If not, that's everything I had for us this night. Thank you for joining, and I'll talk to you guys later.
Thank you.
All right, no problem. No problem. Take care.
Bye.